So, so if we forget about environmental health for a moment and just think about how do you figure out the effect of an exposure on outcome, like a standard approach is, let's say, regression. So how many of you are familiar with regressions? So maybe most of you are familiar with regressions, but so in a regression, what are the assumptions in a, let's say, a linear regression? So if you have an exposure and an outcome, so this is the thing that we are interested in. So if we want to estimate that, let's say we'll do a regression. So then what are the assumptions for doing that regression? So if I look at the data set, if I have the units of observation, so if I have this, so I have some values here, right? So what are the assumptions for doing a regression? So if I do a standard linear regression, how does it look like? So to do this, what are the assumptions? So what are you assuming here? So we are trying to model the relationship between an outcome and an exposure. So what are your assumptions behind doing this? So what do you want to figure out? So you have, so this, if I plot this data, so this would be E on this side and O on this side, and you have these data points, right? So you have n observations. So what are the assumptions? So one assumption is linearity, because we have specified this form. This is linear in what? So this is something very confusing to a lot of people. This is linear in what? So what is the meaning of linearity? Linearity means if one variable is increasing, the other variable increases in a same rate. So this is linear in what? So if I write this, so let's take another equation. And let's take another equation. So this is, if this is, let's say, equation 1, 2 and 3, what is a linear regression, what is not linear? So equation 1 is a linear equation or not? It's a linear regression. Number 2, is it a linear regression or not? Equation number 2, is it a linear regression or not? How many of you think it is a linear regression? And how many of you think it's not a linear regression? What about number 3? Is number 3 a linear regression or not? See, this is the very basic steps of regression. So you have to, before you do any kind of further analysis, you need to figure out these things or have these things clear. Is number 3 a regression which is linear or non-linear? It is non-linear. So now you look at the 3 equations and tell me that it is linear or non-linear in what? So by that I mean, so what is so if you take a linear function, so let's say the standard, so that is the linear relationship, the standard linear relationship that you have learnt in school, right? So so that linearity is in the parameters, right? So what are the parameters in this equation? So if you take y equals mx plus c, what are the parameters? Slope and intercept. So a linear regression or a linear equation has 2 parameters. One is the slope, one is the intercept. So that defines a function which is linear in its parameters. So this is it's little bit confusing because you might think that y and x are linear. So based on this equation, the relationship between y and x is linear, right? Now let's say if I have a function like this. Is this linear or not? If let's assume that 1 by x equals some w. You can do that, right? So 1 by x is a variable. You have the values of it from your data. You can construct another variable which is 1 by x. So if I write it now, so y equals what? So m times w plus c. Is this linear or not? So the linearity is in terms of parameters and not in terms of variables. So when you talk about linear regression, it is because the functional form is linear in parameters. So it is a plus bx plus c w plus whatever. So here the parameters are alpha naught and alpha 1, but they are not linearly set up. So that's why this is a nonlinear regression. This and this both are linear regressions. So that is the first assumption, that we are assuming that it's linear. So that is done. So next what? So what other assumptions do you need for this? So what other assumptions do you need for the linear regression to work? Normality. Okay, so I'll put it here, we'll come back to this. What else? Homoscedasticity. Okay, so that is just equal variance. What else? There is a very fundamental assumption which is more important than any of these. Sorry? Independence of observations. So what is independence of observations? What do we mean by independence? What is independent of each other? So if you have a data set like that where you have exposure variable measurements and outcome variable measurements, where is the independence of, like whatever independence, you tell me where is the independence coming from, who are independent of each other, what is this assumption? So are O and E independent of each other? What is the meaning of independence? So you forget about the regression part. What is the meaning of independence? Sorry? One person. Why don't you go? Yeah. So the probability of some event. So when you talk about independence, let's say the probability of A given B is A, or I mean you can write it the other way. So probability of A and B is, so given that B has happened, it has no meaning on, or no impact or no information on whether A is happening or not. So that is the probabilistic version of independence. So in this case, where is the independence coming from? What are independent? In this assumption, when you say independence is the assumption, what is independent? Each observation is independent of each other. What does that mean? So if you have in the same probability term or information terms, having information on one of the data points doesn't give you any information about the other one. So that is independence. And that is the most, one of the most, I mean, among all of those, that's the most important assumption. So once you have that, once you have these four, okay, so this is fine. So the observations are independent. This is for observations. Homoscedasticity is what? What is the equal variance? Variance of what? Variance of the residuals or errors. So if we have this, so O equals some function of E plus some error, right? So error is it's the things that are coming into the observations because of your measurement or some other sources. So f of E is, in this case it's a linear function, but you can have nonlinear or whatever. This is the part where the homoscedasticity, so the errors have equal variance across other variables. So what about normality? Why is that required? So how does a regression work? So what are you trying to do? You're trying to fit a line through the data cloud. And for doing that, what are you doing? Like, what is the process of getting it? OLS. What is OLS? So there are multiple lines which are like this. Why do you think that this line is the best line? So if I have multiple lines, there can be lines like this. I have to find the line that does something. So by does something means, let's say you try to minimize the error in what you are fitting. So how do you define error? So if you have data points and you have any line, so at this point there's an observation here and you are missing it by this much. So that is the error, right? So this is, if I take this to be yi, so first observation, and this is what you are predicting. So this is the yi that you are predicting. So then this is the error. So you will get this error for all observations. If you have n observations, you will get that. Now the error can be positive or it can be negative. So in this case it is a negative error, this case is a positive error, right? So we want to make sure that the sum of squares of the errors are minimized. So if that's what you are minimizing. So if I square this and if I sum it from 1 to n, this will be a function of what? So how do you minimize a function? So So let's say y was some beta naught plus beta 1 x, right? So if so this is xi, yi. So you are trying to minimize what? So this is what you are trying to minimize, right? So this will be a minus. This is a function of what? This is the sum of squares of errors. Anyone has any doubts about that? This is the sum of squares of errors because yi are your observations and this is what you are approximating it by. So this is the sum of squares of errors. So this goes from 1 to n. What are the unknowns in this function? Beta naught and beta 1. Right? So you know yi, you know xi's. So beta naught and beta 1 are the parameters. So you need to find the value of beta naught and beta 1 so that this is minimized. So how do you minimize a function of parameters? You differentiate and then there's one more step, which is the second order differential is maximized for this to be a minimum. So these are the parameters, right? I can do this differentiation if I mean by standard methods, right? Beta, you differentiate once by beta naught, once by beta 1 and you can get a function, right? I mean you can get your estimates. Any issues with that? So you can differentiate this, standard algebra, standard calculus. Any doubts about that? You will get a beta naught hat and a beta 1 hat, right? If I minimize this, this gives me, minimizing gives me beta naught hat, beta 1 hat. Any doubts about that? Up to this. So you have got your estimate, which is what? It's an ordinary least square, it's a linear regression. So an ordinary least square estimate of beta naught and beta 1. Have you used normality in any, up to this point? So you don't need normality. So this is a common misconception that happens for estimating the parameters of a standard linear regression. You don't need the normality assumption. So why? But it is needed for something else. But are you clear that for estimating a normal linear regression parameter, you don't need the assumption of normality? Whether it's the observations or the residuals, you don't need normality assumptions. An ordinary least square is a pretty good, it has been imposed upon it by years of statistical teaching that normality is an assumption. It does not require it. Anyone has any doubts up to this? Because this is fundamental concept. You do not need normality assumption for estimating the parameters of a linear regression. I just showed you how to do it without using, there's no normality assumption here. So why do you need the normality assumption is this will have some confidence intervals. Right? How well are you estimating the beta and the beta naught and beta 1? Even then you don't need normality assumption. Because you can do this by something called bootstrapping or resampling. Forget about distributional assumptions. If I resample from my data and I can generate data sets from my original data and I can get an empirical distribution of beta naught and beta 1. And that will give me the 2.5 and the 97.5 without making any assumption about normality. But we still use normal distribution assumptions. Why? Because if you see your, let's say a regression output from R or whatever, the regression table that comes out from your regression, that has these t values or your p values and the corresponding t. So what is that t distribution? So a t distribution is normal divided by square root of a chi-square random variable. So all of these distributional assumptions are to get approximations to your standard errors and confidence intervals. So that's where the normality comes in. So if you have a large number of samples, the distribution tends towards to normal. So when you have those t distributions in your p-value tables, that's where it is getting used. But you can do without it. So it is not an hard and fast assumption. It is not required at all for a regression. Yeah. No, normalization is something else. I'm talking about the normal distribution assumptions. So if you are assuming that your errors are normally distributed with 0 and sigma square, normalization is something which is different. That's a standardization of the variables, right? We don't need the normality assumption as it is stated here. So any questions? So we need independence. Linearity is assumed because we are using that function. Homoscedasticity, again, that's equal variance. Normality we don't need. So to do this estimation, what will happen now if these assumptions are broken? So linearity is still fine because we still want to do a linear regression. What if independence is not there and homoscedasticity is not there? Can you do this minimization? So the minimization was what? It's a function of beta naught and beta 1. So if you are using calculus, the calculus doesn't care if you have homoscedasticity or independence or whatever. It will just minimize the function. So to do the estimation, you don't need it. You don't need any of the assumptions. So please ask questions if it is not clear. So to do this minimization, standard calculus tells you that you can minimize this with respect to beta naught and beta 1, get these estimates. None of these assumptions are featuring in any of that. So why do we need assumptions? Or what happens if the assumptions are broken? So the place where the assumptions are required is because of the variance estimation. So these would have some confidence intervals, so some lower limit and upper limits for both of these. To correctly estimate that confidence interval, you need these assumptions. Doesn't mean that if the assumptions are broken, your estimates will be incorrect. So your estimation, so there are two things. One is whether the estimate is unbiased, so whether it is deviating from the truth, and the other thing is how precisely you are estimating the coefficient. So all of the homoscedasticity assumption or the independence assumption, the problem is created here, not here. So when will the independence assumption be violated? When will the independence assumption be violated? Repeated measurements is one. So what is happening in that? If you have repeated measurements, so let's say so if you have individual 1 and you are measuring their blood pressure once, twice, over time. So what was the independence assumption? What did it mean? So if you have n observations, what does independence mean? One doesn't give information about the other, or one doesn't depend on the other. If you have the blood pressure measurements of one individual over time, what is happening? If you are measuring my blood pressure today and my blood pressure tomorrow, so today's blood pressure would give information about tomorrow's blood pressure for the same individual. So that's the dependent structure in this case. So in a longitudinal study, for example, you would have dependent observations because you are observing the same thing over time or in the same unit. So what are other examples? So let's take this picture. So this is a map. You can forget about the legend for now. But what happens in a spatial data? So if you have regions which are more likely to have a certain, let's say, an outcome or certain predictors, then having information about one individual in that cluster is going to give you information about another person living in that same cluster. So let's say you are doing village level sampling or school level sampling or hospital level sampling. The individual units that you are observing your data on are not going to be independent because of that clustering. So there is some level of homogeneity within a village or within a school. So then if you sample two individuals from the same village or two individuals from the same school, their observations are not going to be independent. So this is a standard, let's say, a cluster level analysis or spatial analysis, because within a smaller spatial unit, individuals might be dependent. I mean, the information that you are getting from one individual is going to give you information about another individual in the same unit. So that's why the independence assumption is broken. So what that means is, if you assume independence in a non-independent or a dependent setting, so if your observations are dependent, what happens is you are estimating variance incorrectly. So the assumption of independence is going to reduce your variance or increase your precision. So in reality, in this case, if you have dependent observations, your variance of estimation, because let's see, if you have 100 individuals, they are independent, the amount of information they are giving you is, let's say, some 1 unit of information. If out of those 100, they are coming from 10 different clusters, so 10 people from 10 clusters, that one cluster of 10 people is going to give you same information, right? So just very crude. So instead of getting 100 units of information, you are getting 10 units of information, because within each cluster they are giving you same information. So the information you get from a clustered sample is going to be less. So 10 clusters, 10 individuals each, 100 observations and 100 independent observations. The number of observations is the same, right? But the information you are getting is less in the clustered situation. So your precision should be less in the clustered situation. Any doubts about that? I can repeat it. Yes. So the estimation is not affected at all, because as I just said, I mean that thing doesn't have any. I mean, you can just minimize it again. Right. So this equation here, there should be a sigma square here, right? Because it is, I mean, so I can do it like this. So that sigma is constant if you are making a homoscedasticity assumption. Every error variance is same. So the variance of EI is sigma square. That is a constant, so it doesn't play a role in the estimation. If the sigma square is not the same, so if it is sigma I, so if this is not same, then there is a problem, because these are not the only parameters. So there's one more parameter here. And if you make an assumption that this is the same, then you are going to do what? You are going to get an imprecise, or you are overestimating your precision. If you are assuming that your 10 individuals, so if I summarize those 10 clusters and I get 10 observations, I can do an analysis on that because the people in the same village or same school is giving me same information. So I can, instead of looking at 10 different observations in a school, I can, it's same thing if you take the mean of that school and do the analysis with 10 observations, you should get the same, that's the information that you're doing. So by not taking care of independence or assuming independence and not taking care of the correlation structure, the covariance structure, you will get narrower confidence intervals. So if you don't take care of clustering, or if you don't take care of the spatial clustering or the dependence structure, you are going to get confidence intervals which are narrower than what they should be. So, and what would happen in that case? So you are overestimating your precision, right? So in that case, you might get significant results when they are not really significant. So when do you get let's say a statistically significant result? When, let's say, the confidence interval, so if beta naught, the hypothesis was beta equals or beta naught equals 0. So if this was 0, so if your confidence intervals are here and your beta naught hat is here, that's a statistically significant result. So when you are assuming independence when the data is not independent, you will get this. When in actual situation, it probably should have been this. So your beta naught hat would have been here and your confidence interval would have been wider. So it is important to take care of the dependence structure in your data to avoid this situation, to estimate variance correctly. So usually what would happen is the beta naught hat wouldn't change its position. It's only your confidence intervals become wider or narrower. Yeah. So prediction has nothing to do with this. So this is entirely estimation problem. That is a different thing. Yeah. So you don't need to make assumptions about dependence in a prediction problem. The prediction problem is you have your data set, you split, you train your model, test it out on the left out data set. That makes no assumptions about dependence or normality anyway. It's a different problem. Prediction problem and estimation problem are different. So this is entirely for an estimation problem. So similarly, homoscedasticity, if you have unequal variance, you have to put that into your model. So you have to, let's say, instead of doing, so this is the exact same thing. So if you have a WI, which is the weights for the variance. So it's 1 by sigma square, let's say. So by inverse weighting based on their variance, you can take care of, even if you don't have a homoscedasticity. So unequal variances can also be taken care of. So in a spatial data set, so if I assume that within each, let's say, sub-district or within each village, there's some kind of clustering. So if you get one outbreak data in one village, it's probably more likely that you will get another one from the same village. So then when you see your outbreak data, they are clustered, right? So hotspots or whatever. So then the predictors in those units are also potentially correlated. You are getting similar kind of meteorology, similar kind of land use, and that is giving rise to outbreaks or similar characteristics of people living in that unit. So then they are not dependent, they are not independent anymore. So now you have to take care of that dependent structure in your analysis. So when we talk about, let's say, spatial regressions, see, the basic structure is the same. I want to make this point that whatever you do is like whether it's time series or spatial regression, longitudinal data, logistic, linear, Poisson, everything is just a regression. That structure remains the same. So y equals some function of x plus error. How you model that f and depending on what your y is, that's all variations. But it is still a regression. Everything is a regression. Everything is a regression, is just by breaking assumptions you are doing different regressions. That's it. So I'll give you these because there's no point making slides again. So this is a very nice tutorial about how to do spatial regressions. But I want to make sure that you understand why you are doing these things, because there are a lot of R codes and details about how to do it. But it is very important to understand what they are doing, like the underlying concepts. Any questions? So this is the basic regression. Any assumptions about why? What is why? So if you have outbreak data, or let's say yesterday's example, number of hospital admissions, what is y then? If y is the number of hospital admissions, are you making any assumptions about y? Sorry? It's a count data, yeah. So let's take some examples. So number of admissions, let's say blood pressure. What else? Birth weight. What else can be there? So let's say whether a person is hypertension or not. 4 different types of variables. So blood pressure is measured in what? It's a continuous variable. Birth weight, again, continuous variable. Hypertension is 1, 0. A number of admissions are counts. But all of them are linear regressions. So the simplest case is if you have a continuous variable, the blood pressure and birth weight, this is the simple equation, right? So if I am looking at the effect of PM 2.5, this exposure doesn't change. I mean, you can change the duration or whatever, so I'll just leave it like this. This is the equation for blood pressure or birth weight. So what is happening if it is changing to admissions, number of admissions? How will this change? Have you done logistic regressions or let's say Poisson regressions? How do you deal with a situation where your outcome is not continuous? How would you transform a 1-0 variable? So let's say if you have a data which is hypertension yes no for individuals. So the first person has hypertension, second person has hypertension, third person doesn't have hypertension. How would you transform this? How do you get the logit function? So let's say this is another one, this is day. So day 1 to a number of admissions. There can be 0, 3, 1. So if this is my outcome or this is my outcome, I can put this in straight and do a linear regression. So there is problem in that. What is the problem? No, but you can do the regression, right? I can put these values in and do a regression. Because this works for continuous variables, it would work for any kind, whatever data you put in, it will work. The problem is that a linear regression like this, it is giving you what? An intercept and a slope. So let's say the intercept is here and the slope is positive. So it will look like this. And what is this? So this is x and this is y. So if you have this kind of a setup for these variables, at some point of time, the y's would become infeasible. So what is the meaning of y in this case? So it is either hypertension, yes or no. And this is number of admissions, which is count. If you do a linear regression, everything is possible. It is not only 0 and 1. Right? So if I fix the value of PM2, if I do this estimation using 1 and 0 as the outcome, then if I put a value of PM2.5, is there any guarantee that it will return a 0 or a 1? It is not guaranteed, right? Because it's a continuous function. It will give whatever value it wants depending on this. So one way to do this is you convert this in such a way. So what is the range of values for this? You forget about the error. What are the potential values for this part, the right hand side? So beta naught plus beta 1 PM2.5, what are the potential values of this? Sorry? Yeah, so anything. So this range is minus infinity to plus infinity. Any doubts about this? So this part. Your y's are 0 1s. So they are not matching on both sides. So if we make the quantity such that it goes to this real line, then it is fine. Then we can do a regression. So what is the easy way to do this? So y is 0 and 1. So there are only two values. So how do you get from here to here? So this 0 and 1, why does it come as 0 and 1? Because you are assessing someone for hypertension. So it depends on a probability of whether that person is hypertensive or not. So what is probability? So probability of being hypertensive or not hypertensive. So let's say this is some P. So what is the range of values for P? Range of values of P. The probability of being hypertensive. It's 0 to 1, right? Probability goes from 0 to 1. So this is from 0 to 1. So now some basic algebra. So if I divide this by, so if I divide P by P1 minus P, what is the range of this? P is a fraction, 1 minus P is also a fraction. So if a positive fraction. So divide a positive fraction by another positive fraction, the range will be 0 to infinity. Right? So this goes from 0 to, so I've still not reached here. So how do I go from here to here? You take a log, because it has to be a positive number to take a log, and that would unbound it. So the log of P by 1 minus P is unrestricted. So now this matches. So if we model this instead of the actual y, then you get a logistic regression. So this is how you get a logistic regression. So what are those y's, zeros and ones? Because this doesn't look like 0 and 1, right? So what is this? The p is the risk. So p by 1 minus p is the what? Odds. So log of odds. So you are modeling log of odds of an event. So why are we getting ones and zeros is because these are Bernoulli events, right? So it happens with probability p or not with 1 minus p. So this is how you get logistic regression by modeling the log of odds. So what if now it is counts instead of 1 zeros? So the counts are what? The values. They're usually whole numbers and it can go from 0, 1, 2, 3, 4, right? So it can be. So how do I get this? So this is again, the C is positive. So one step to go from here to this, if you take a log, it will become this, right? So if I use log of the counts, then again this matches with this. So that is what? That is a Poisson regression. So you see how so you are just breaking those assumptions one by one and you are getting this from the same linear regression, you are getting logistic, you are getting Poisson. Now let's say, the independence assumption we already broke and that can be taken care of by using clustered analysis, which we'll talk about a little bit. The clustering can be here, it can be here, and it can be in the birth weight, blood pressures, all of those examples as well. So taking care of what your outcome is, that is one thing. So whether it's a linear or a logistic or a Poisson, taking care of the independence assumption is through the clustering, which is whether you account for the cluster or not. That is more of a dependent structure, so more to do with the variance. So in a spatial regression, you can have any of these, right? So you can have all of these things in a spatial format. Because let's say you are doing number of hospital admissions in a particular sub-district. Or in, let's say if you are doing a clinical field study, you can look at number of cases of, let's say, cancer or whatever. So the left-hand side is changing depending on what outcome you are studying. The spatial distribution can be there for all of them. So whether people in certain villages are more likely to be hypertensive than not. So how do you take care of the clustering? So any questions about this part? So regressions are just, it's one basic structure and then you start modifying it. So right now I have only modified this. Right? So linear, logistic, Poisson. I can modify this as well. Right now this is linear. I can make this non-linear. So there are ways to do that. So the linearity assumption can also be broken. And any assumptions about E, so like the independence and the homoscedasticity, that can be broken. So we'll show you how to do it in using things called fixed effects or random effects analysis. So have I made sense? I mean, are you getting it that it's only one regression that you start with and then you keep breaking things in one way or the other? So three things to break. One is here, one is here, one is here. And that gives you every analysis. Any questions? So in a spatial situation, you will have, so I think Ajit showed you that, let's say your data has columns which have the geometry, and so that you can plot it on a map. So this is what a spatial data would look like. So you have these codes for each of the, spatial unit. You have a ward number. So this is data from UK. And then you can have clusters like nested things, like district. Within that you have sub-district. Within that you have villages. So similarly, you have country, which is England. Within that they have a county, which is Merseyside. Within that they have a Liverpool district. Within that they have a ward. So there are nestings. So the nesting is again doing what? It is breaking which assumption? Independence, because it is just a different kind of structure. I mean, when I said clusters, there can be multi-level clusters. So if I just have village information or school information, then all children within that school are, the observations of those children are dependent. But here there is everyone within the same country there's one level of similarity. If you come down to the county, then there's another level of similarity, but it is nested. So the ward is nested in the district, district is nested in the county, county is nested in the country. Right? So, and then you have these predictors. So these are individual level variables. These are district level or ward level, like spatial variables. So this is age 60 is what is the proportion of people who are more than 60 years of age? Proportion of unemployment. So remember when we said aggregate data, that number of hospital admissions. If you get the number of hospital admissions, you can also get, let's say, the proportion of people with age in a certain age group. That proportion you can get at the aggregate level. It will not be individual level data, but you can also get this. So the percentage unemployed. The lat long, and so these things are centroids. Males and the proportion of males, I think that's, I forgot but those are mentioned here, the exact value, the meaning of the variables. And then there's a geometry here, which is why you plot it on the map and see. So how do you account for this? So there is some clustering or dependence. How do we account for the dependence in the same regression? So just as an example, so this is the percentage unemployed, and you will see that there are chunks which are, so like this is a very big chunk, but since you have only one data for one cluster, it would show up as uniform. So maybe there are not too many people living here, but your percentage unemployment will be the same for the whole district. It's the district level or the ward level data. So what is showing up here is, let's say districts here, there are some hotspots where the percentage of unemployment is quite high. But they are clustered here, like there's a yellow here, there's an orange here, there's some yellow and orange here. This part is very, very purple, so it is very low. So there seems to be some spatial clustering just for the unemployment. There may be certain neighborhoods which are clustered together which have more unemployment than others. So one way of taking care of the dependence is by using random intercepts or mixed model approach. So I'll go back to the same thing. right? So this is the regression. I'll remove the EI for a moment because this is what we are dealing with, the systematic part. So this doesn't vary with I, these parameters. The beta naught and the beta 1, which is the slope and the intercept, they don't vary with I. Now let's say you have a cluster. So if you have village 1, village 2, so there are k villages, let's say. I can make this vary by village. So if you think of so if this is the population line, for one village you can have like this. This is fixed intercept, so you have one intercept for every one and different slope for every village. Right, so this is village 1, 2. So there can be another situation where the slope is the same, but every village has its own intercept. They start off different. So again 1, 2, 3, 4. And then the last thing is anywhere. Right, so this is, you are changing your intercept and your slope by village. So how do you do that is, if you imagine this to be some so now if this is dependent on, so there's a village specific intercept and there's a village specific slope or a cluster specific slope. So what that means is your village level intercepts are just randomly distributed around a population level intercept, which is, in this case, let's say the slopes are same. So if the population level intercept is somewhere here and the beta naught 1 and the beta naught 2, so they are randomly, they are distributed around the population intercept. So this is something called a random intercept model. So where your intercepts are changing by cluster, but your slopes are not. This is, your intercepts are not changing, your slopes are changing. So there is some population level slope which is some beta 1 and your village level slopes are around that. And both changing is this situation. So by doing this, so how do you do this in, let's say R is, you will get the code here, but you are using this information to model the variance better. Your village level or the cluster level information that you are getting. So what you are supplying to the code is that, because the code doesn't know which are dependent, which are not. So you are saying that everything, all observations that belong to one village, treat them as dependent. So they have information about each other, right? So that's the mixed approach, which you will do for the spatial regression. Any questions? So I'll give you all of the, you will have all of this. The last one, the geographically weighted regression, that's a bit more complicated. That's based on the proximity of observations in space. So that same variance, or what you are, the main issue is the variance, because the information is similar. If you are getting close to each other, you have the same information. So to model that variance, there's something called a geographically weighted regression. So you are weighting, so things that are clustered together, you are giving them more weights while estimating the variance there. So that's a little bit, it's not a mixed model approach. So the mixed model approach or the random intercept approach is this multi-level modeling approach. The geographically weighted regression is modeling the variance in a different way. So there are three options to do the spatial regression. We mostly use the mixed model approach. The problem with the geographically weighted regression is if there are multicollinear, the issue of multicollinearity, which is if your predictors are highly correlated, then it runs into a problem. But it's a valid method to use if you have distinct variables or not very correlated variables as predictors. But usually we use because we are not really interested in a mixed model, you are not really interested in the district specific or the village specific estimate. You want to estimate variance correctly by removing, so it's more of a nuisance. So you don't want to estimate village level intercepts. You want to get the population level intercept by accounting for the variation correctly. So that's why the mixed model approach is a better approach, because you don't have to bother about estimating. If you have 50 villages, you don't get 50 intercepts. You assume that those 50 intercepts are randomly, normally distributed around some population level intercept, and you report the variance of that. So you deal with lesser number of variables, parameters.